Okay, in this short video, I want to cover some of the highlights in Chapter 7. And Chapter 7 deals with binary integer programming, which is a type of declaring variables and using constraints to reflect typically yes or no types of decisions. Now, if we look at some of the problems we've worked on already this semester, for example, in the PSI problem that we did, we actually formulated that as a binary integer programming problem, whereby each decision variable was either sort of a 0 or 1, a no or a yes in terms of whether or not we should assign a particular order to a particular plant. So we've already had the little experience in terms of sort of formulating and solving these kinds of problems, but in this chapter they give a few more nice examples in terms of how you can use, again, either binary, meaning 0 or 1, or integer, which means must have answers in whole numbers. You can use those approaches for decision problems. So let's just walk through some of the examples really quick and talk about some of the highlights. So, and let me take care of this as I always have to. So again, they're great for dealing with yes or no decisions. Should you do something or not? Should you undertake a fixed project? Should you build a plant or a factory or not, or a warehouse? Should you assign a particular order to a plant? Should you choose this location or that location for a particular factory or whatever? Also, things like, should you make this kind of a set of assignments to an individual or not? So there's a lot of sort of yes or no kinds of go or no go, or fixed cost kind of things that can be reflected in this way. So the first example is this California manufacturing company, and they don't yet have any plants or warehouses in Los Angeles or San Francisco, but that's what you're trying to help them make a decision on. They've got a limited amount of capital, and also there's some ideas in terms of they should only build at most one warehouse, and also they should only build a warehouse if indeed a factory is also going to be built in that same city. So that's how the problem is laid out in the chapter. And so basically what we're going to do is attach a binary variable to each of these decisions. In other words, yes or no, should we build a factory in Los Angeles? Yes or no, should we build a factory in San Francisco? Yes or no, should we build a warehouse in LA? And yes or no, should we build a warehouse in San Francisco? And so this problem is it's got 4, 0, or 1 variables. Now, if you wanted to, you could enumerate all of the possible solutions to this, and there would be 2 to the 4 such solutions. So it wouldn't be a huge number, but very quickly, if the size of the problem will get very huge. For example, there's no way you could have enumerated all 200 possible decisions for the PSI project that we did in the last couple of weeks. So what's also given as far as data associated with each of those decisions is the amount of capital required if you move forward with that particular capital investment, and also what the net present value of the project would be in terms of savings and so forth. So again, we're setting up these decisions, we're declaring them as 0 or 1 variables, and in each case the 1 represents actually building the particular factory or warehouse, and 0 represents not doing that. So you have to kind of be clear up front in terms of how you're encoding those yes or no decisions. Now this is an algebraic formulation of the problem, and all we're doing here is we've got the 4 variables, and we're trying to maximize our total NPV. And so you can see that expression of the objective is maximize NPV equal to 8 times x1, 5 times x2, and so forth. So again, that 8 million is the net present value if in fact you do build that factory in LA, but you're going to get 0 NPV otherwise. The first constraint is the limitation on the amount of capital. We only have 10 million available, and each of the projects requires a different amount of capital investment, so we can't exceed our budget. And then also the declaration that we want to have at most just 1 warehouse. In other words, like, don't build 2. You can build 1, in San Francisco, or one in Los Angeles, or not build any at all. And that's what that second constraint does. The last couple of constraints are interesting because what they say is that if you are going to build a warehouse, only do it in a place where you also have decided to build a factory. So what that means is only if x1 is equal to 1 can x3 take on a value of 1. That's that constraint. x1 is greater than or equal to x3. So in this way, again, you're only allowing one of the variables to take on a value if the other one take on a value greater than 0 if the other one has necessarily taken on a value of 1. So that's the case for both, again, building a warehouse in San Francisco as well as building a warehouse in Los Angeles. So, and we're going to declare all the variables to be binary. And let me show you really quick what this particular model looks like. So again, we've got our data up here. We've got the various net present values for each of the 4 possible projects, if you will. We've got the capital expenditures for each of the 4 possible projects. And then down here in yellow, we've got basically the binary variables associated with each of those 4 possible projects. Now, for example, the capital spent is equal to a sum product of the capital required for all of the 4 projects times the amount, which is the capital required for each different project. So again, if you look at that, it's this combination of the builds for both the warehouses and or the factories. So anyway, and again, there's a constraint there which says that capital spent must be less than the capital available, which is in light blue, which is, again, that's just data given. Also down here, we'll say that the maximum number of warehouses we can have is at most 1. And then we've also just simply got sort of representations here to say that you can only build a factory if, in fact, you can, in other words, this variable of building a warehouse in Los Angeles can only take on a value of 1 if, in fact, the variable for building a factory in Los Angeles has also taken on a value of 1. So one other thing I'll note here, by the way, is when we run the model, of course, we're maximizing our net present value. We're changing the variable cells which correspond to the 4 different options. And we've included all of our constraints we just discussed. But you'll notice also that there are constraints added which are, in fact, to declare the variables to be binary. So it's in the constraints is where we declare or require a set of variables to take on, say, binary values, 0s or 1s. And so again, just like any other time, you can add a variable and you can say, well, it's these variables here, and we can declare them right here to be binary. And then that's requiring that those be, that's how you ensure that you only get back binary solutions to the problem. Okay? So upon solving this problem then, let's go back to the slides. We can also use Risk Solver to evaluate a number of scenarios. In this case, we can range our available capital from 5 up to 15 million and have it optimally solve for each of those various cases. It's kind of like doing a data table, but it's repeatedly solving solver. And then from that, again, you can glean a number of observations. They originally planned to say, let's just make 10 million available, and if indeed that's the case, your best NPV is down at that 13 million. But it allows you to start doing, again, classic what if kinds of analyses. For example, the optimal solution was just to use $9 million of capital. But again, if you try to use even less than 9 million, you can very easily see how bad the net present value drops off. And if you maybe even just push the capital up a little bit, you'll see that, hey, there's a big jump in terms of NPV for just throwing in an extra $1 million on top of the 10 that you were already planning. So these are the kinds of what ifs that you can query with respect to really any optimization problem that you model, and this is just one form of doing it with a binary problem. The second example in the class or in the chapter is this Taser Corp, and this is a very straight up and down problem, and it falls into a category of problems we call knapsack problems. And knapsack problems, you imagine that someone has given you a knapsack that can hold only a certain amount of weight, and you're going to go camping, and so you've got a limit on how much weight you can put into that knapsack. And there's a bunch of different food items you could potentially put into the knapsack, but if you tried to put them all in, it would be way too much weight. So there's kind of a classic problem that is, if each food has an associated like caloric value, then you would ask yourself, well, what's the what's the optimal set of food items to put into that limited weight knapsack so that I maximize the amount of caloric value that I have in my food altogether. So that's sort of the kind of a lay description of this type of an optimization problem. So in this case, they've got a certain amount of capital available. So you almost think about that as being the size of the knapsack. You've identified 5 different projects, and you can kind of think of those as the five different foods, basically. And then what's also given is, in fact, the expected profit. This bottom row here is the expected profit for each of the different 5 projects. And you can kind of think about that as the caloric value of the possible 5 foods that you can put in the knapsack. And so the formulation is very straightforward. You're trying to maximize the profit, but you're subject to a limitation on your capital investments. And again, if we shell out and take a look at the Excel file on this, then indeed we can almost kind of ignore those 2 rows that I've got highlighted right there. Really, all that matters is the top line, which is the R&D investment, which again we're subject to a constraint on, and the expected profit, which is sort of like the caloric value of those different projects, if you will. And again, so to take a look at the solver model, it's very straightforward. It's just saying, give us a 0 or 1 in terms of whether or not we're choosing to do the projects or not. We're declaring that as binary, and we have we can't exceed our budget on capital investment. And so it's, again, very straightforward problem. Real quick, we'll cover a couple more. This one is interesting. It's an Airways crew scheduling. And here's the way this problem works is that they need to cut, they have basically 11 flights that need to be covered across the nation. And we've got 3 crews that can be assigned to cover those flights. And we want to make sure we cover all the flights with only those 3 crews. So in a way, it's kind of a feasibility project. Now all the crews will start here in San Francisco, and here are the various legs of the flight. There's one that goes from San Francisco to Seattle, and then there's another leg which flies from Seattle back to San Francisco, and then there's one from Chicago to Seattle. So every one of these arrows represents a flight that must be covered. Now, clearly, if a flight crew flies from San Francisco to Seattle, then they can fly any of the legs out of Seattle to help cover, other legs. So let's take a look at how this is kind of formulated. So each column here corresponds to a feasible sequence of flights that a flight crew could cover. So for example, this first column would be one possible route. You could have a flight crew that starts in San Francisco, goes to Los Angeles, LAX, and then flies from LAX back to San Francisco. In other words, they got to start and finish back in San Francisco. So that's one possible sort of route for a crew. Here's another one, San Francisco to Denver in the second column, and then Denver back to San Francisco. And then here's one that starts running them all over the place. Number 4 here, the column, would be a crew going from San Francisco to Los Angeles, then Los Angeles to Chicago, which is ORD, and then Chicago to Denver, DEN, and then Denver back to San Francisco. So you could string those together as well. And even as you get into number 11, for example, 9, 10, 11, and 12, you're actually stringing together a total of 5 legs, 5 different flights into this model. So again, if we go to the Excel file, take a quick look at that, and indeed, here's the problem. We've got those columns, which again, each one represents the particular sequence of flights that a crew could do, starting in San Francisco and ending up back in San Francisco. We also have for each of those things an associated cost. So, in other words, if you're going to have a crew that just goes from San Francisco to Los Angeles and back, it's going to cost a total of $2,000. Whereas again, look at this route number 11. You've got someone going to 5 different legs, and that costs $8,000. So the constraints are that you must in fact cover all 11 legs. So we're looking for a combination of crew routes that at the end of the day covers all 11 legs and does so at a minimum total cost. So the constraints, or excuse me, the variables are down here in yellow, and they're just binary in terms of whether or not you are going to sort of light up one of those crew schedules or not. And you can see the solution here. We've actually lit up 3 different crew schedules. And our constraints here are saying, look, we have to cover this flight. So, in fact, are we covering, does this include, or the sum product of this row times the decision variables, which are the ones that you've actually chosen, that must equal, the sum product of those two gives us a value here in column 0. So let me just kind of show you a quick example here. If I zero all of these out, then I'm not covering any of the legs that I'm required to cover. But if I go, well, let's put them on this 5-leg flight, that this column 11, then check it out. That identifies exactly which of the legs are being covered. And let's say we also do San Francisco, this first one, which is the real simple out and back from San Francisco to Los Angeles. Wow, we've covered a few more, but check it out. We're actually now covering this leg twice. So again, you set up this optimization. It's right now you've got, if you think about it, you've got 12 different binary variables. 2 to the 12 is a very large number. So if you were to try to sit there and peck out a lot of different combinations, you'll be sitting there a very long time until you even reach one that's feasible, much less one that minimizes the total of the minimizes the total of the cost. So again, we set it up. We open up Solver. We're trying to minimize the total cost. The variables are in yellow, the flight sequence that we've decided to choose. Those must be binary. That's one of our constraints. We have to at least cover the all of the legs, which is that total greater than or equal to at least 1. And then we've got a limit. We've only got 2 crews available to do that. So, it'd be, you could set up a model like this and then say, wow, hey, can we cover it with 2 crews? If not, hey, can we cover it with 3 crews? Yes, we can. Hey, what if we had a 4th crew? Would that, and we solved it for that? Would it result in a cost that was even less than using 3 crews? So indeed, you can set it up and ask Solver to just simply work out that final, very complex decision right there. So the last one that we want to cover here is an extension of our WinDoor. And the only thing different now, we've looked at WinDoor for several chapters now, but now we have a one-time setup cost. In other words, if we decide we are going to make some doors, we're going to incur some expenses to set the production facility up to be able to start making doors. So it's, again, you incur that cost no matter how many doors you decide to make. And that's very different than the variable cost of making a door. So this is where you bring in sort of, these true sort of fixed one-time costs rather than just simply a proportional cost that's based on the number of units. And so let me just show you that one really quick. It's and this is, by the way, a very common model. You're going to see it a lot in terms of distribution systems, production decisions, and so forth. And in this model, again, what's different now, we have our good old unit profits like we had before, but now we've got this additional data, which is the setup cost. In other words, if you decide to make any doors at all, you're going to have to incur a $700 cost to set up the facility to start being able to produce doors. Same thing, you've got a $1,300 fixed cost to set up and start producing windows. So everything else is the same in the problem except this down here. And it's kind of using a version of the first example that we saw today. And that is the amount that you're going to be able to produce, which this was our original set of decision variables every time we've looked at the problem up to now. But now you're going to add a constraint that basically says the following. If you can only start producing doors if in fact you have declared you're going to have a setup to produce doors. So watch what happens when I change that from 0 to 1. You'll notice that this value went from 0 to 99. Now if you look at that, the formula says it's 99, which is basically, the 99 is just some big number. In other words, you could put in 1,000,000 right there. And all it's saying is, that's just the combination of this big number, whether it's 99 or 1,000,000, times 0 or 1 is basically going to allow you to produce doors or not. In other words, we know in this problem we're never going to produce more than 99 doors, so we have to just choose a number that's at least as large as 99, or at least as large as the most number of doors we could ever produce in 1 week. But again, if I set that equal to 0, that's 0 times 99 is equal to 0, and it will not let us declare any doors to produce. This is just basically having the model make sure that you at least pay that fixed cost. So again, we set this model up, we'll zero it out and take one quick look at it. And again, here's what it looks like. And this is a real common model that you see where it's now using a combination of, in this case, binary variables in terms of whether, yes or no, are we going to set up for doors, yes or no, are we going to set up for windows, and variables in terms of like the number we're actually going to produce. So again, we're still trying to maximize total profit, but now we have two sets of variables: the number you're actually going to produce of doors and windows, and whether or not you're going to take the setup for doors and whether or not you're going to take the setup for windows. And again, the units produced, this first constraint, the units produced, you can only do that if in fact you have incurred the setup. And so it's basically, again, in this case, C14 must be less than or equal to C16 is what's really kind of going on there. And we've got a maximum in terms of the hours used at each factory or at each plant. And we've got binary assigned, or constraining the 0 or 1 constraints to be binary in terms of whether or not we set up to produce doors, whether or not we set up to produce windows. And then now we're actually requiring that we're only going to produce an integer number of doors or an integer number of windows. So we set that up and we solve it. Oops, wrong one. Let me go back over here to WinDoor and see if I can bring that one up and solve it. Well, I've got a little problem here because I've got actually several worksheets open. So let me just close those up and not save those. Taser Corp. And I will close the Airways one. So, and let me just now bring it up for the revised WinDoor. And we in fact will do that solution. And sure enough, it turns out that the thing to do is now only to set up and produce the windows. And if you do that, you'll have a maximized total profit of $1,700. So in this case, it says you're better. Remember, before the solutions were always some number of doors and some number of windows. In this case, it's saying, no, it's not worth it to set up for the doors. You just, with the limited number of hours and the fixed cost for setting up doors, it's just simply not worth it. So I hope this has been helpful, and we will see you in class then next Tuesday. Thanks, and have a great weekend.